Okay, colleagues, so hello and welcome back. Today I want to talk about free will and quantum mechanics. An interesting topic in all sorts of ways. Widely discussed and also, I would say, widely misunderstood. Now, this is one of those topics that often comes up during class, and there's never really enough time to talk about it properly. So for once, I thought I would take my time and just try to collect my thoughts and give a certain presentation of what I think. Now, I have been thinking about this issue for a very long time. So I do have a strong opinion, and also I think that my opinion is well grounded. And sort of for my own, so to speak, internal mental purposes, I am comfortable, well assured, if you want, of my conclusions. Now, the usual disclaimers and caveats. I am not really an expert, and I haven't really published any books or articles on the topic. So I think I do have a strong and educated opinion, but I would definitely advise everyone to take everything I say with a grain of salt. I probably should stop repeating this every time, but I did, in the past, change my opinions in response to intelligent criticisms and questions from students. So if any of you can point to some mistakes in my reasoning, I am, by all means, open to changing my opinion, even though I kinda don't really expect my opinion to change. It's kinda, in general, a big topic in philosophy of science. We, as humanity, have something that we consider to be a body of knowledge, and if you dig deep down, you will see that we don't really have any firm grounds. So it's kind of an interesting and a slightly paradoxical situation. Namely that we, and I as well, believe certain things, believe them seriously or take them seriously, believe them passionately maybe even if you want. But at the same time, it is important to keep in mind that we may be wrong, or in this particular case, I may be wrong. And I think to hold this something of a contradiction I shouldn't say contradiction, a tension. To hold this tension in your consciousness, in your head, is one of the skills of being a philosopher. So having the audacity to put forth a definite proposition and hang on to it, while being open to the possibility of it being challenged at a later point in the future. So I don't really want to continue this line of thought, because that's not the plan for today's discussion. But at the same time, I think it's important to keep this in mind and sort of to remind myself and you of this issue. Now, to go back to the topic at hand, let me maybe try to summarize what I think the gist of the argument is. So, as you know, an important guiding thread in all of my videos, all of my presentations, is the idea or topic of naturalism. I don't think I'm unique in this respect. I think that in some sense, the issue of naturalism is the foremost intellectual issue of our time. One way to illustrate this issue is by considering that from a certain textbook presentation of the so-called unity of science, all of this wonderful world that we experience with our hopes, fears, anxieties, desires, the beauty and the ugliness, that actually at bottom, all of this is just physical stuff. Matter in motion, or some version of that statement. Particles bumping into each other, according to deterministic mathematical equations, or to be maybe slightly more up-to-date in terms of physics, fluctuations in the quantum fields interacting with one another, according to the Lagrangian of the standard model of particle physics. But either way, the issue is that this world of meaning and significance that we see around us seems to vanish when we look at our most basic and, it seems, most secure descriptions of reality in terms of the underlying physical phenomena. To take a concrete example, how a cherished hope in my head bottoms out in simple, straightforward biological neuronal firings in my brain, complicated quantitatively, basically because there are so many neurons in the head, but not really qualitatively. Each neuron is fairly simple. So again, the hope being reduced to the neuron firing, and the neuron firing being reduced or reducible to organic chemistry, and organic chemistry, one way or another, being reducible to the quantum mechanical description of reality. Elementary particles, or again to be more precise, fluctuations in the quantum fields, seeking lowest energy states. The ultimate point being that the meaning, the beauty, and the morality of our everyday, phenomenological, if you want, experience vanishes at the level of the fundamental mathematical description of the four known forces governing the interactions in the basic quantum fields. Okay, so that's the problem. Why should we care, though? What is the significance of this problem? So first of all, I'm sure a lot of people will simply find this naturally fascinating. But for the rest of us, why should we care? And the context in which, for me, these discussions usually spring up is the context of moral and political philosophy. Let me also parenthetically mention that teaching in the International Relations Department has taught me, given me a certain interesting perspective, a perspective according to which political philosophy is far more important than ethical or moral philosophy, more important and primary, in a sense that considerations of morality seem to take precedence when we are, when we find ourselves in a small community of like-minded people, within a family or within a village. But when you get to the multicultural nation states, and more importantly, the global world order, and I think it's a deep mistake to forget that the individual communities exist at the mercy of this global world order. So anyway, at the level of the global order, it is politics, and to a large extent international politics, that rules the day. And the individual ethical life exists in the context of, or if you want, as permitted by, this global world order, by which I mean a certain international balance of power, without going into details of how exactly this international balance of power works. But again, how do we connect this, basic physicalist materialism with the moral and political universe? And one immediate connection that springs to mind is, of course, nobody will be surprised to hear this, is Thomas Hobbes, with his attempt to derive the rules of politics from a very thin physicalist picture of the universe as matter in motion, and of living creatures of being a certain type of matter in motion. Again, cannot resist to parenthetically mention that, of course, in our post-Darwinian biological and neurophysiological framework, it is hard to not be sympathetic to what Hobbes is trying to do. But again, the upshot is, if we take Hobbes seriously, is that since on the level of basic description, which for Hobbes is matter in motion, and for us is energy fluctuations in the quantum fields, broadly speaking the same, I would say, there is no such thing as meaning, morality, purpose, etc. And yes, the usual quote, "Whatsoever is the object of any man's appetite or desire is that which he calls good, and the object of his hate and aversion is what he calls evil, there being nothing simply and absolutely so." So again, to reiterate, no meaning, no purpose, no morality, at least no objective morality and no objective meaning or purpose. No values with a capital V, as Nietzsche might have said. And also no freedom of the will, and therefore no genuine moral responsibility, the kind of responsibility for which Christian theologians thought it appropriate to send people to hell for all eternity. Okay, so that's what we have in front of us. An interesting picture, a troubling picture to a lot of people. So what does any of this have to do with quantum mechanics, right? And again, to state the issue as briefly as possible, a lot of people, I would say a great number of intellectuals, take refuge in the ambiguities and uncertainties of the textbook quantum theory to try to save themselves from this bleak materialistic worldview of Thomas Hobbes. Now, just to be on the safe side, I'm obviously giving you a tendentious presentation from my own point of view. So when I say things like most or a lot of people, I don't think I have actually done a proper research. It's more of my general impression. But be that as it may, certainly some people at least want to use, again, the ambiguities and uncertainties of the textbook formulation of quantum mechanics to save themselves from the materialist challenge of Hobbes or any other materialist, physicalist thinker. Let me also signal there's another important issue which I do not plan to talk about today, and that is the issue of emergence. The idea that even though basic description of reality is in terms of mathematical regularities, framed in terms of the interactions between quantum fields and the four fundamental forces, still some philosophers would say that it is possible that, so to speak, higher level phenomena of their own nature, sui generis, to use a Latin phrase, could emerge, again, as I said, on a higher level of description or higher level of reality. So something like, even though there's no morality on the level of electrons, but still there could be a place for objective morality in the world of human beings. Again, broadly speaking, I would say that this whole question falls under the rubric of emergence, and I probably should definitely do a separate video on it. So having made this footnote, having issued this, so to speak, IOU to myself and to the listeners, let me move on to the topic at hand. Okay, so 12 minutes into the talk, finally I'm getting to the gist of the matter, which is quantum mechanics, right? Okay, so as usual, let's start with a broad stroke, basic overview of the land. Lay of the land. What is the battle disposition? So, what is quantum mechanics? Why quantum mechanics and not general relativity or some other theory? So, again, the basic textbook presentation of this topic is that quantum mechanics is our most basic and most certain, most accurate and most verified picture of reality. And again, this is true, quote-unquote true, from, if you want, at least a sociological standpoint. If you go to the physical departments of the leading universities in the world, or let's say engineering departments, or microbiological departments, this is the broad consensus that we have today in the world. And again, the predictions of quantum theory have been verified to a spectacular degree of accuracy and precision. Of course, Humeans among the listeners might question these procedures of verification, quote-unquote, but we don't have to really go into that right now. At least in a sense of, in the kind of language game that we play in the university, we have to, so to speak, institutionally take this picture for granted. Or if not for granted, at least with a high level of credibility. I wonder if I should remind myself and the listeners that Cartesian and Humean type skepticism or solipsism or relativism is, technically speaking, irrefutable as far as we can tell. And again, barring Humean and Cartesian considerations, if you want from a Wittgensteinian language game standpoint, I think we can safely say that contemporary quantum field theory lies at the very foundation of our contemporary mainstream academic paradigm in 2020, if you want. Let me also parenthetically say that, as a professional philosopher and as a Sextian skeptic by persuasion, I don't feel any particular urge to disagree with the status of quantum mechanics. Yeah, it's been verified, and I am fairly pleased with the way it's been verified. So let me just say, I will assume for the rest of my discussion here that we know quantum mechanics to be true for a fact. Again, to be completely pedantic, of course, we cannot know anything true for a fact, but as far as we can, quantum mechanics comes as close as possible. Okay, digressions. Let's get back on track. So, an important disclaimer, I'm not a physicist, so I'm not exactly authorized to give you the full story of quantum mechanics, but I hope I can give at least a reasonably accurate general overview of what the issues are. And I would be more than happy to direct you to materials and sources authored by professional physicists who know what they're talking about. Stanford Encyclopedia of Philosophy might be a good place to start for people who want to double-check my presentation. Temptations to sidetrack. Idea for a future video. Why should we trust Stanford Encyclopedia of Philosophy? An interesting question. Definitely worthy of a separate video. Okay, back to quantum mechanics. Okay, so just for fun, quantum, in the word quantum mechanics, refers to the fact that certain fundamental properties of our best description of reality at the fundamental microscopic level seem to only come in discrete chunks, so to speak. So when I say seem to only come, I'm referring to the result of experiments and observations. So in some sense, the only way, or the best way for us to make sense of the data, is that the world is fundamentally discrete in certain respects on a fundamental level. Like, for example, electrons in an atom can occupy only certain particular energy levels, and these energy levels would be multiples of a basic energy level. Why is this so? How to derive this? Not important right now. Why does the Schrödinger equation only have integer solutions? Look it up, okay? Now, is this important? Probably not, but I just wanted to get this out there. It's kind of a long and fascinating story with Niels Bohr and Albert Einstein. Actually, Einstein's discovery of the photoelectric effect, which demonstrates this quantum nature of reality, is actually what got Einstein the Nobel Prize. So some of you just might want to check this out from the standpoint of, basic curiosity. Back on track. So okay, quantum mechanics is quantum, so what? So far nothing, this tells us nothing. Now what is really important and what we need to get to is the Heisenberg's uncertainty principle. Unscharfes Prinzip, or unscharfe Relation. So here is finally the crux of the matter, so to speak. Now classical mechanics, Newtonian mechanics for example, was strictly deterministic. You have laws, mathematical regularities, and if you imagine some kind of a vast intelligence, Laplace's demon as it came to be known, that knew the position and the momenta of every particle in the universe, this vast intelligence, this demon, could in principle predict everything that's going to happen and also retrodict everything that has already happened. So for this vast intelligence, there would be no past, no future, and obviously no free will. So this was the classical picture. And for a long, long time, this is what the debates were around, the materialistic debates. And let's say 100 years ago, let's say in the year 1900, the hope was that life could not be explained in simple physical terms. That there was something like the élan vital, for example, of Henri Bergson, that went beyond this merely physical causation. And somehow you could show that animals, and especially human beings, operate outside of this framework. Now again, advances in molecular biology, the discovery of the DNA, and the progress in neurophysiology, what Francis Crick calls the astonishing hypothesis, I think have mostly laid to rest those kinds of hopes. Of course, there are some people who are holding out, pointing to the fact that we do not yet have a complete understanding of how the brain works. And it's true, but on the other hand, I would not really bet on that. I would not bet on our understanding of the brain being false, in the sense that yes, the brain is extremely complicated, but the basic mechanisms are clear. And again, the fact that you can have a glass of wine, and this will impact the way that your allegedly immortal, immaterial soul behaves, is in some sense proof enough that we live in one world. I'm obviously aware that a lot of people will not be satisfied with this simple explanation, but again, for the sake of the argument, let's just go back to quantum mechanics. So if we've given up hope with this élan vital, and if we think, okay, life is just a motion of limbs, and therefore automata have artificial life, as Hobbes says, apologies. So if we think that life is simply a chemical process, and ultimately all chemistry is a form of, physical phenomena, then, people who want to challenge the physicalist and the naturalist picture could try to look for limitations of the physicalist picture, not in terms of, let's say, biology not being explicable in basic physical laws, which was a strategy of 100 years ago, but kind of no longer really viable, I think. So now we want to say, oh, but there is something interesting and unusual going on the basic description, at the basic level of description of physical reality. And here's where we get to the Heisenberg's uncertainty principle. So as we said, in classical mechanics, Laplace's demon, knowing all the position and momentum of all the particles, can predict and retrodict everything, basically the whole history of the universe. But Heisenberg's uncertainty principle tells us that you cannot simultaneously know the position and the momentum at the same time to an arbitrary level of precision. In fact, the more certain you are of a particle's momentum, the less certain you are of its position. The more certain you are of its position, the less certain you are of its momentum. Now, again, if you didn't understand that, don't worry too much, because the point is that what ultimately Heisenberg is saying, or I should say what ultimately is the conclusion that we draw from the way quantum mechanics is formalized today, is that there's a certain necessary incompleteness in our understanding of how nature works. Let's say the results of certain experiments can never be predicted with 100% accuracy. Actually, it's more dramatic than that. There are certain fundamental features of every experiment that can never be predicted with greater than 50% accuracy. Okay, let's pause here and let's ask a question about the relationship of ontology and epistemology. Namely, ontology, what there is, and epistemology, what can we know. Is Heisenberg's uncertainty principle, is this epistemological or ontological? So is it the case that we simply do not know, or is it the case that, let's say, the universe is actually random at bottom? And again, the standard textbook interpretation, and this is going to be the first time in today's talk where I disagree with the standard textbook interpretation. So the standard textbook interpretation is that the uncertainty is ontological. More importantly, the standard Copenhagen interpretation of quantum mechanics, championed by Niels Bohr, famously asserts that there is no such thing as a definite position or a definite momentum of the particle before we make the measurement. Let's say in the famous double-slit experiment, although it's a slightly different setup, but some people might be familiar with this, the Copenhagen interpretation, people like Niels Bohr would say that the electron, or some other particle, let's say electron, is neither a wave nor a particle. That in some sense, there is no fact of the matter. Once you make the measurement, you can make the electron behave like a particle or like a wave, but in and of itself, it is neither. It is in a superposition, the technical term is, but it's important to remember that a superposition is not just a combination. It's not like, oh, it's both a wave and a particle. No, it's kind of something completely different. Completely different and, most importantly, uncertain and undefined. Now, this seems to be a very bold assertion on the part of Niels Bohr. And attentive students will no doubt come up with a couple of questions to this position. And this could potentially be a very long discussion. And we could talk about Bohr's own understanding of philosophy of science, and specifically his positivist leanings, this tendency to not really ascribe any kind of reality to unobservable phenomena. And you could argue, and many philosophers of science have argued, that Bohr's position basically amounts to saying that when I turn my head around, I have absolutely zero grounds for saying that the moon exists while I'm not looking at it. It's an example that's been used by Einstein in debates with Bohr. One could say that this is basically an idiosyncratic position on Bohr's part, but again, without trying to make this a 10-hour-long video, let me try to summarize the basic points and to, try to place our feet firmly on the ground. So first of all, again, Heisenberg's uncertainty principle seems to be sufficiently verified. Like, nobody really expects that tomorrow we will find some kind of an experimental technique which will allow us to actually measure both position and momentum, or, let's say, the spin of a particle in two perpendicular axes, which is another example of this uncertainty principle. So at least the epistemological uncertainty looks like it's here to stay. Okay, so what can we say about the ontological uncertainty? Is it the case that the universe is random and sort of that the electron does not make up its mind before you measure it? Now, here again, the matter is not so simple. And I have to say, I think there's a lot of confusion. And there are a lot of, so to speak, red herrings. People, chasing off into random directions. So let me try to focus the issue. So, notoriously, Albert Einstein debated with Niels Bohr. And Einstein had this famous phrase that God does not play dice with the universe. But one has to understand, Einstein was not simply, complaining. Einstein actually had an argument. And Einstein's argument was formalized in a paper, very famous paper by Einstein, Podolsky, and Rosen, EPR paper. And the point of the paper is that if quantum mechanics actually is simply an incomplete picture of reality, and the uncertainty is due strictly to our ignorance, this can be tested in an experiment. And what we have is a fairly long and gruesome story, highly illustrative in many ways, of how science deals not only with logical motivation, but also with pathological motivation, as Pierre Bourdieu calls it. I'm not an expert, so I'm not the one to tell the story. You can look this up. But basically, people who at various points in history occupied this heterodox, potentially deterministic position, that is, held on to a potentially deterministic interpretation of quantum mechanics. So at various points in their career, this would refer to Louis de Broglie, Albert Einstein, Erwin Schrödinger, and then, very importantly, David Bohm and John Bell. So basically, all of these people were not taken seriously by the mainstream of the physics community. And the answer as to the question why is kind of complicated and shows, let's say, a human, all too human side to the professional physics community. So, for example, the fact that Niels Bohr seems to have been an extremely charismatic person and had a way of influencing people without necessarily persuading them with logical arguments, but simply on the strength of his charisma. Or John von Neumann, a hugely important mathematician, providing what turns out to be a faulty proof that a deterministic explanation of quantum mechanics is impossible. Again, von Neumann's proof contained overly restrictive, unrealistic assumptions, but simply because von Neumann was so influential and well respected, most people did not bother double-checking his results. Or the fact that on the other side of the divide, David Bohm, for example, was a member of a communist party when he was young, and this led to all sorts of problems I don't even want to discuss right now. Okay, you can look this up. Now, I think all of these are very interesting examples of how one should never forget that scientists are also humans, and they also have motivations, which have to do with honor and prestige and maybe even grant money and that kind of thing. An important lesson in all sorts of respects. But I do not really want to overstate or overblow the case, because at the end of the day, I think that the pragmatic attitude that is taken by most professional physicists, which goes something along the lines of shut up and calculate, like the equations work and I'm not going to worry about what's the fundamental description of reality. I can understand why people take this standpoint. And in some sense, maybe that's the way it should be. That's exactly the way it should be. Because there's physics and then there's philosophy of physics, and these are two different disciplines. And you want the people who do the calculations, who, so to speak, send the rockets to space or build hadron colliders, you want them to be preoccupied with the equations and not necessarily with philosophical issues. Yeah, okay, potentially an interesting discussion may be a topic for another video, but again, let me go back to the gist of the argument. So what I'm trying to say is that for good or for bad reasons, the Copenhagen interpretation was taken too seriously, was taken basically as the final statement. Until in the 1960s, John Stuart Bell, a very important physicist at that time working at CERN, Centre Européen pour Recherche Nucléaire, actually came up with a way to experimentally test Einstein's ideas. So came up with this hugely important result, Bell's theorem, or Bell's inequalities. Again, completely mainstream, completely foundational to the way quantum mechanics is taught and understood today. And so later, a French physicist, Alain Aspect, or probably Alain Aspect, actually carried out the experiments. Now, his experiments weren't perfect, and so the first, as they say, loophole-free experiment was actually conducted in 2015 with polarized photons, if anybody wants to look this up. And basically what happened is that, in some sense, Einstein was proven wrong. Okay, and so this is actually where I want to pause and try to explain what's going on. So, Einstein's hope was that you could account for the seeming or apparent indeterminacy of quantum mechanics by the appeal to what Einstein called hidden variables. That actually you do not know the position and the momentum of the particle, but the particle actually does have a definite position and momentum. It is simply an epistemological limitation of your measuring apparatus. Now, Bell's theorem and Aspect's experiment found a very interesting, ingenious way to test this. It's really fascinating, kind of technical at the same time. I think the basic takeaway point is fairly simple to understand, and maybe I will do a separate video on it. But right now, let me just state the conclusion. And the conclusion is that the kind of behavior, the kind of correlations that we observe indicates that the behavior of fundamental particles cannot, in any shape, matter, or form, be explained by any local, important word, local hidden variables theory. So it absolutely cannot be the case that an electron, let's say, has a definite position and momentum as inherent properties, local inherent properties of this particular electron. Okay, so Einstein wrong, Bohr right, right? No, it's not that simple. So even though Bell's inequalities, Bell's theorem, rules out the possibility of the so-called local hidden variables, actually, what still remains on the table, and John Bell was a proponent of this particular theory, or I should say interpretation, is you can have a complete description and a complete deterministic picture or model of the quantum universe, which reproduces all of the effects, including this impossibility of precise measurement, but again, at bottom is completely deterministic. Now, I'm sure you could imagine many such systems, but the simplest one, and the one that John Bell actually advocated himself, came to be known as the pilot wave theory, or sometimes as the de Broglie-Bohm pilot wave theory, or simply Bohmian mechanics. Now, a short technical aside. Some people could say, okay, so Bell's inequalities are violated. How can you have determinism? Well, Bell's inequalities presuppose that you cannot have local hidden variables, but you can have non-local hidden variables. So especially in the case of entanglement, this is what Einstein called spooky action at a distance. Don't worry if you don't understand this, I'm just, short side note. So this spooky action at a distance is a certain kind of quantum mechanical influence which does not carry information, however, which does measurably propagate faster than the speed of light, possibly instantaneously. And in the pilot wave theory, this is actually the pilot wave itself. So all the particles are approximately classical with definite positions and momenta, but the particles are guided by a pilot wave, and this is incidentally the resolution to the double-slit experiment. The idea is that we do have both a wave and a particle, but the wave, the pilot wave, travels possibly instantaneously, certainly faster than the speed of light, according to the results of the experiments. And on this view, Heisenberg's uncertainty principle comes from the fact that a macroscopic measuring apparatus always necessarily interferes with the state of the quantum mechanical system. Now, if I ever make a more detailed video on the pilot wave theory, a very important aspect of the pilot wave theory is the so-called assumption of quantum equilibrium, of an equilibrium initial condition, so to speak, some sort of a stochastic distribution of the initial condition of the pilot wave itself, so that the randomness in the experiments comes not from the actual randomness of the universe, but from the randomness which is inherent in the deterministic pilot wave. Now, again, demanding philosophy students could say, okay, but why does the pilot wave have this property? Why is it in the so-called quantum equilibrium, which is supposed to be, broadly speaking, analogous to a thermodynamical equilibrium? And I want to say, you have every right to be worried about this, but, this problem of initial conditions is a huge problem in all of philosophy of physics, and nobody should really expect any simple solutions to this problem. So, for example, when you talk about the Big Bang, the initial conditions of the Big Bang, or if you're a fan of some kind of a multiverse interpretation of the Big Bang, for example, infinite inflation, or Penrose's conformal concyclic cosmology, there is always a problem of initial conditions at some point in the past. Again, sidetracks of sidetracks, but if you imagine a nagging kid, annoying kid problem, a child who just keeps asking the question, why? One has to understand that this is a basic feature of our model of explanation and understanding of the universe, that our picture always bottoms out in a certain regularity for which we do not have any deeper explanation. Broadly speaking, similar to how Isaac Newton, when he discovered the law of gravity, discovered the equation, but very explicitly acknowledged that he does not know where the equation comes from, actually. And if you say, well, the equation comes from some other equation, well, you could say, okay, where does this equation come from? Still, I think this issue of quantum equilibrium, even though it's technical and most people will not be able to understand what the hell I'm talking about, I think it should be taken seriously. But to me, at least from a philosophical standpoint, it seems to be a lesser mystery than, let's say, attributing random chance to the universe, like ontologically, although, opinions may differ. Now, all of this is terribly complicated and technical, and I'm sure I've lost like half the viewers by now. But let me try to draw some preliminary conclusions. So, the idea was that if the universe is determined by physical laws, sort of if we believe in a physicalist or naturalist picture together with Hobbes, then free will and meaning cannot be salvaged in any shape, matter, or form. And the hope was that the randomness at the root of quantum mechanics, more specifically Heisenberg's uncertainty principle, could somehow save us from that. So the conclusion is, no, Heisenberg cannot help you. Or at least there is no deep, compelling reason why Heisenberg has to interpret it in an ontological rather than epistemological fashion. That is to say, the results of the experiments clearly show our inability to know the complete description of the quantum mechanical system, but the pilot wave, whether it's true or not true, provides a plausible picture of how a strictly deterministic process can give rise to this sort of experimental observation, experimental outcome. So to really, really oversimplify, is determinism true? We don't know. Big surprise. Ancient philosophical problems do not have any straightforward knockdown solution. We do not know whether determinism is true or false, but there is no reason to think that determinism is false, and people who think that Heisenberg and Copenhagen disprove determinism simply do not understand pilot wave. Pilot wave may be false, but it, at the very least, provides a methodological, plausible counterexample of how determinism could be true, and yet we observe something like Heisenberg's uncertainty. To say this once again for the third time, I don't actually think that pilot wave is true. There's a lot of things that rub me the wrong way. Now, it might be true, but I would not want it to be taught to students as orthodoxy in any shape, matter, or form. But I think any thinking person thinking deeply about these issues, and definitely all philosophers of physics, should at least know about the existence of the pilot wave as an alternative interpretation. To come at this again from maybe a slightly different angle, one could say, yeah, Alex, but which one is true, pilot wave or Copenhagen? And the answer is, this is not a very well-formed question. because the experimental predictions of the Copenhagen interpretation and of pilot wave interpretation are exactly identical. So right now, this moment, there is no way to experimentally distinguish between the Copenhagen interpretation and the pilot wave interpretation. So I'm not saying that one is truer or more plausible than the other. What I am saying is the strong assertion that the Copenhagen interpretation is the only possible interpretation, namely that nature is random and inexplicable at bottom. This interpretation cannot be taken as truth with a capital T, because there are alternatives, namely pilot wave. Kind of an underwhelming conclusion. So, okay, at the end of the day, what about determinism? What about free will? What about meaning? Is it true? Is it false? Are we free? Does life have meaning? Good questions. In fact, excellent questions, I would want to say. And I do think that these questions can be answered. And I do agree on some level with Thomas Hobbes in that physicalism and the assumption of absence of free will makes a lot of sense. But this is an argument for a completely different video. The basic thing I tried to show today is that these questions of freedom and meaning cannot, in any shape, matter, or form, be definitively answered by appealing to the phenomena of quantum randomness. And that's basically the point of today's video. Okay, so I hope this was fun and illuminating, at least to some extent. At the same time, apologies, I guess. The video is kind of long and kind of technical. But at the end, I do hope that I've managed to hit the sweet spot of being not entirely superficial and actually presenting at least the bare bones of some of the arguments. So basically these 30-40 minutes worth of time are my thoughts on the relevance of quantum mechanics to questions of free will. And my thoughts are, it's irrelevant. Quantum mechanics is completely irrelevant to the questions of free will. Or at least quantum randomness and Heisenberg's uncertainty is irrelevant to the question of free will. These 30-40 minutes are the ones I never have in class. So here is finally what I would have said about the issue if we had more time. Now you've heard it, and I hope it was worth your time. I hope it was fun, illuminating. And I'm looking forward to continuing this dialogue with my students. And for now, thank you so much for your attention, and I'll see you around. Take care.